Hello everyone and welcome to WE-MEDIA Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is On the Quest for an Optional DC-DC Isolated Gate Drive Supply Topology, Formula E and WE-AGDT Transformers. Our speakers are Eleazar Falco and Emil Nierges. They will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation, but nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve the event. You will also receive the link to the presentation in the next few days, and the recording will be available at our website shortly. But now I will hand over to our first speaker for this session, Emil, and I wish you an exciting presentation.
Thank you, Marie. Hello, everyone. Here is the agenda for this session. We are going to talk about auxiliary supply in gate drive systems, DC-DC topologies for gate drive auxiliary power supplies, and a brief comparison between these topologies. And Eleazar is going to take over and talk about WE-AGDT reference design and Formula E. So now let's get into the topic, starting with the auxiliary supply for silicon carbide and IGBT gate drive systems. Today on the market, we see two ways of implementing gate drive controls. One of them is using the transformer to actually transfer the control signal. I would say the old way here on the left. How it works, the IC controller sends the signal through the transformer over the isolation barrier to the switching device gate. Therefore, the transformer role in this is to pass through a signal and not power. While with the new technologies, we can see more and more that this task is taken over by the IC driving itself with included isolation barrier. However, the IC still require an isolated power supply for the secondary side to provide the VDD and VE voltage. Therefore, a transformer is used to generate the isolated auxiliary voltages. We can still call this transformer a gate drive transformer due to the tight specification related to the application. For a better understanding, here is an application example for powering an AC motor load. The high power brushless electric motor needs a minimum 3-phase alternative AC current or power source, but the available power might come from a DC bus, direct current form, like after a PFC stage or from battery. Therefore, a circuit called power inverter will provide the conversion DC to AC using a system of switching devices into a full bridge configuration. Each switch is controlled by a gate drive IC, and each of the gate drive IC needs its own isolated power supply. And here comes into play our power transformer, which offers the needed power and isolation. Now let's review the most popular DC-DC topologies in gate drive applications, and we will start with push-pull. The push-pull topology is one of the easiest to implement with a simplified design working on a fixed 50% duty cycle and without the need of output backstage. Therefore, output inductor is not required. During the small dead times, the output capacitor will take over, providing the output power. The transformer works in so-called forward mode. Therefore, the power is transferred instant, so there is no need to store the energy. Therefore, we can have a transformer in a smaller size. There are very few components, like 2 low-side switch devices on the primary that can be easily integrated in the controller IC, output rectification diodes, and capacitor. Again, there is no output inductor and no feedback loop components. There is no need for a snubber due to the very low energy storage on the leakage inductance. With this topology, we reach an efficiency around 85 to 92%, but of course, there might be other losses involved, like linear pre-regulation or post-regulation, and losses due to voltage doubler rectification stages. For the main disadvantages, we can say it's running in open loop. Therefore, the output voltage rails are unregulated, and the input voltage needs to be tightly regulated. There are many push-pull reference designs on the market, and here's just an example with 24-volt input voltage in cascade switching devices that offer multiple outputs, very low profile, fixed duty cycle, and no output inductor. The flyback is essentially a buck boost topology that it's isolated by using a transformer as a storage inductor. The transformer not only provides the isolation, but by varying the turns ratio, the duty cycle can be balanced and optimized for the output voltage. The flyback is the simplest and the most common of the isolated topologies for low power applications. The main advantages are wide input voltage range. With primary side regulation, can achieve well-regulated output voltage rails within 5%. With just a simple diode and a simple capacitor, we can easily create multiple outputs, assuming that the transformer have these extra output windings built in. Fast transient response, mainly because the flyback topology and the mode of operation, discontinuous conduction mode and boundary, and of course, they come with reasonable good efficiency, around 86%, and with good regulation, that most of the cases do not need a post-regulation. As for the disadvantages, the transformer needs to store the energy, therefore this impacts the size. So we will need a bigger transformer compared to a push-pull. There is a trade-off to take in account efficiency versus EMI and immunity, and needs carefully to make designs for the best performances. Here it's an example of reference design using LM5180 with primary side regulation. Input voltage range 18 to 36 volts, output voltages plus 15 and minus 4 volts at 130 milliamps. No auxiliary winding is needed and no optocoupler. The buck converter with isolated output takes the advantage of a very simple buck topology, and just by adding another winding with a set of output rectification diodes and capacitors, we can achieve or create an isolated and regulated output. The main advantages are the wide input voltage range. The isolated output is indirectly regulated and following tightly the non-isolated buck voltage. Additionally, the non-isolated output voltage actually comes for free. Again, we have fast transient response and efficiency that we can achieve about 75–88%, varying quite a lot with the operation conditions. Disadvantages: performance is very sensitive to the transformer leakage inductance. Trade-off regulation with efficiency versus EMI immunity. Duty cycle practical limitations below 50%, and to achieve reasonable performance where we can mitigate the leakage inductance effects, I would recommend to have a 30% maximum duty cycle. There are many reference designs on the market, but not many address well the gate drive application, especially because of the common mode transient. Here it's one example with input voltage range of 10 to 17 volts, output voltage of 15 and -8 volts with about 2 watts of power. It also takes the advantage of the non-isolated output voltage of 3.3 volts to supply the primary side of the driving IC. The half bridge, like push-pull, is based on a forward converter topology, therefore is simple to design. The transformer do not need to store the energy, can be in smaller size. Also, there are less number of windings than a push-pull, therefore simpler and less parasitic interwinding capacitance. Low component counts, similar to push-pull, but just to note the difference that one of the primary switch is now on the high side, so it needs a bootstrap voltage. Again, no snubber is required and efficiency range around 85 to 92%. As for disadvantages, it runs again in open loop, therefore the output voltage rails are unregulated. The input voltage needs to be tightly regulated. This topology is one of the most seen on the market with many reference designs. And here it's one example with input voltage of 15 volts. It has two sets of output voltages, plus 15 and minus 7.5, with about 2.5 watts of power that could serve both the high side and low side of the half bridge main application. The Resonant LC, it's a half bridge topology that uses a resonant technique to reduce the switching losses. Due to the zero voltage switching, it also achieves low EMI emissions. The transformer do not need to store the energy again. Usually, an LLC application is quite complex. It's frequency variable, requiring a lot of design resources and relatively high number of components compared to a half bridge. But by minimizing the operating range of the LLC, like to run in the open loop, always at resonance, therefore fixed frequency and low voltages, DC-DC, allows to simplify the design, and then remaining needed features could be integrated in a controller IC. This is a very common mode, a very high common mode transient immunity, since it can use a transformer with a larger leakage inductance, resulting in much smaller primary to secondary parasitic capacitance. Good efficiency, 85 to 92%, taking into account very low interwinding capacitance that we can achieve, and as a result, handling well the leakage inductance. As for the disadvantages, needs careful designs for the best performances. Output voltages are unregulated, and specific techniques are needed to keep the output voltage with good regulation. Input voltage also needs to be pre-regulated. A reference design example runs an isolated open loop and provide dual outputs, plus 20 and minus 4 volts, up to 6 watts of power from 24 volts input, featuring very low interwinding capacitance of 1.5 picofarads. Let's make a summary, side-by-side comparison on DC-DC power supplies topologies for gate drive systems. Within the topologies that we have discussed, push-pull, flyback, isolated buck, half-bridge, and resonant LLC, if we compare for the same specification of input and output voltages and power levels, and as well for the same size, this table gives a general idea on how they typically perform regarding CMTI efficiency output voltage regulation. Please note that this is just for constant input voltage. We expect to achieve the highest common mode transient immunity with the resonant LLC, and this is due to the acceptance of high leakage inductance. Therefore, the transformer can be designed with very low interwinding capacitance. On the other hand, the isolated buck needs very low leakage, and therefore the transformer will have more interwinding capacitance and will perform not so good regarding the CMTI. As for the efficiency, the resonant LLC, it should be theoretically the best because of the 0-volt switching and recovering energy from the leakage inductance. On the opposite side, flyback and isolated buck topologies will suffer because they need to dissipate this leakage inductance energy each cycle as a power loss. Regarding the output voltage regulations, flyback converter should perform the best as it operates in closed loop, whereas push-pull, half-bridge, and Resonant LC operates in open loop. Please note that this is just a general comparison, and the final performance of each topology depends on how the design is done and optimized for. On another table, we can see a comparison related to the input voltage range, regulated output, and transformer need to store the energy, or in other words, to have a gap. The flyback and isolated buck have the advantage of wide input voltage range and as well regulated output, but they need to store the energy. While on the other hand, push-pull, half-bridge, and LLC, they need fixed input voltage, but no energy storage is required, and the output voltage is unregulated. And with this, I thank you for your attention, and Eliasar will take over now and talk about WE-AGDT reference design and Formula E.
Yes, thank you, Emil, and hello everyone. So in this second half of the presentation, I'm going to talk a bit about WE-AGDT transformers, the reference design, and Formula E. Würth Elektronik is official technology partner of the Formula E team Audi Sport, ABT Scheffler, and as part of this technology partnership, Würth Elektronik has not only supported the team with providing optimized passive components, but also has supported with some design activities. And more specifically with the reference design RD001, which is an extremely compact auxiliary gate drive power supply featuring the WE-AGDT transformers. This design was originally developed for and is currently used in the MGU-05 electric powertrain, which is built into the Audi e-tron FE07 Formula E car, which is competing this season. The reference design is one of the key components in the motor inverter module of the powertrain, where several units of the design are currently used. In addition to try to help the Formula E team to get a technology advantage and a competitive edge in the race, Formula E is also a strong driver of new product innovation at Würth Elektronik. Some examples of that are the red cube terminals in the past and now the WE-AGDT transformers. It's also good to mention that Formula E also serves as a harsh environment testing field for these components. And here we can see the schematic and the basic electrical specification of the reference design. It accepts an input voltage range, 9 volt to 18 volt, and provides regulated output voltage rails of plus 15 volt and minus 4 volt, with a total combined output power of 6 watts, up to 6 watts. These specifications are optimal to drive some of the latest silicon carbide power modules and are also suitable for discrete devices and IGBTs. The design has been implemented with primary side regulated flyback topology, which for these specifications presents some advantages compared to alternative topologies like the half bridge or the push-pull or a resonant design. This is because the flyback does not require any additional input or output regulation stages. It already accepts a wide input voltage range and provides well-regulated output voltages. Despite the energy storage in the transformer, which might be seen as one of the drawbacks of this topology, still a very compact and cost-effective solution can be achieved if the design is done carefully and optimized properly, especially regarding the transformer and operating conditions. And here we can see the output regulation of the positive rail on the left and the negative rail on the right. Regarding the positive rail, we can see a regulation of around 1% for the full input voltage range, and for the negative rail, around 2.5%. And here the power efficiency. At full power of 6 watts and nominal input voltage of 12 volts, we still have an efficiency of 84%. But we can also see how for most of the output power range and for all the input voltage range, the efficiency stays above 84%, which for a low power primary self-regulated flyback is quite a good result. The reference design is also available for you to use in your application. It is provided in 2 PCB layout variants. Variant A, which is a 4-layer PCB design with components on top and bottom sides. And variant B is a 2-layer PCB design with components only on top side. In addition, 2 assembly variants are provided, one with ACQ qualified components and other assembly variant with a standard commercial grade components. The PCB layout files in Ultimate Designer, as well as the fabrication files, Gerber, Pick and Place, are available in the Würth Elektronik website. You can access them via this link here down on the right. And in addition, also a reference design document with all details about the design and experimental results is also available in this link. And just for curiosity, here we can see how the 2 variants of the reference design compare in size with a €1 coin. They are really, really small. Here we can see an example application of a 3-phase power inverter or motor drive. We can see how it is formed with 3 half-bridge stages in parallel, one for each phase, featuring a high side SiC-MOSFET device and a low side SiC-MOSFET device. Each silicon carbide MOSFET has its own isolated gate driver system, as we can see, which is formed by the isolated gate driver controller and by the isolated auxiliary supply. Here we are showing the variant B of the reference design RD001 as an example. Let's see now some of the potential benefits of using the reference design in an inverter application, for example. First, the wide input voltage range allows to power the circuit directly from a variable or loosely regulated input supply, like it might be, for example, a 12 volts battery. The design also provides the possibility to enable or disable the auxiliary supply externally via a microcontroller. Regarding the PSR Flyback IC controller with integrated MOSFET used, in this case LT8302 from Analog Devices, it features important protection functionality like under voltage lockout, overcurrent and short circuit protection, as well as thermal shutdown. In addition to this, it does not require any optocoupler for regulating the isolated output rails, which together with the protection functionality really increases the reliability. Now, another important feature is the high output power up to 6 watts. Here we can see in the formula how the auxiliary supply power relates to the gate drive power losses in the circuit. Basically, when driving the silicon carbide MOSFET device, there are some power losses in the gate drive circuit, and this needs to be made up for or compensated by the auxiliary supply. And those power losses, they are directly proportional to the gate charge of the silicon carbide device, the switching frequency, and the gate source voltage swing with which the SiC-MOSFET is being driven. We can directly see how a higher auxiliary supply output power will allow for a higher switching frequency of the silicon carbide MOSFET device. and high switching frequency can provide the benefits of a smaller size of the solution. But in addition to this, also higher auxiliary supply power can contribute to increase the power density of the inverter. And we can see this, one of the ways that we can increase the power density of the inverter is using SiC-MOSFET devices or power modules with the same size or a smaller size and lower RDS(on). However, the RDS(on) parameter is on a trade-off with the gate charge of the MOSFET device. So lower RDS(on) is going to come at the cost of higher gate charge. But if we have higher power in the auxiliary supply, we can drive these SiC-MOSFET devices with higher gate charge. For the reference design RD001, the product of the gate charge by the switching frequency needs to be below 330 milliamps. Regarding the transformer, it has been designed with low leakage inductance and low DCR. This is with the objective of achieving higher efficiency. Now, why we want high efficiency in the auxiliary supply when it is used in an application of tens of kilowatts? The reason is thermal performance. In order to keep the temperature rise of the transformer and also the rest of the components, like for example of the snubber circuit, as low as possible, so that we can use components of smaller size, and also we don't need any big copper heatsink areas on the PCB. So at the end, we can achieve a very compact solution, like we can see here. And other potential advantage is being able to operate at higher ambient temperatures if the temperature rise of the components is kept low. Another very important parameter is the interwinding capacitance of the transformer. Has been designed very low, 7.5 picofarad. This allows for high common mode transient immunity. We will see next slide in a bit more detail what CMTI is. But high common mode transient immunity will allow the silicon carbide devices to switch faster, which will mean that the switching losses will be lower and we can achieve higher efficiency in the inverter. But not only that, lower power losses also means that we might be able to optimize the cooling system. So reduce the size and the cost of the cooling system is another potential benefit. And in addition to this, also helps us to achieve better EMI performance, because the lower the interwinding capacitance of the transformer, the lower the common mode current coupling between the two grounds, high voltage side and low voltage side. So here we can see one of the half bridge legs of the inverter. We have replaced on the high side device the gate driver system. We have replaced the auxiliary supply and the isolated gate drive controller IC by their equivalent parasitic capacitances across the isolation barrier. In the case of the auxiliary supply, this is the transformer interwinding capacitance. When the high side device switches on, a very high dV/dt appears on the switch node. Now we should note here that the source terminal of the high side device is directly connected to this switch node, and it also serves as the isolated ground or voltage reference of the gate driver system of the high side device. This is going to result that this high dV/dt is actually being applied between the isolated ground on the high voltage side and the quiet ground on the low voltage side. This is going to drive some displacement currents across the parasitic capacitance of the isolation barrier, and this might cause a lot of problems. Distortion of control signals, but maybe more importantly, stressing the controller with high common mode currents. This might lead to erratic behavior of the controller with the consequent loss of control of the silicon carbide MOSFET device. Common mode transient immunity is a measure of the maximum rate of change of voltage, dV/dt, which can be tolerated across the isolation barrier before malfunction occurs. It is measured in kilovolt per microsecond or volt per nanosecond. And now we can easily see how if we decrease or we reduce the parasitic capacitance across the isolation barrier, the interwinding capacitance of the transformer is contributing to it, then we can achieve higher CMTI rating, and the SiC-MOSFET devices, they can switch faster, and we can achieve all the benefits that brings. Here we can see an example of the integration in the gate driver system. This is a half bridge configuration again, but this is in this case for a high power buck boost converter. And we can easily see on the high side, SiC-MOSFET device, in this case a discrete device with a heatsink, the auxiliary supply, and the controller system here. And the same for the low side. Now a bit about the HDT transformer. It has been designed using a really small EP7 bobbin assembly. It has been modified slightly. You can see an extended rail here in order to meet creep edge distances for safety standards. It's a surface mount component, pick and place ready. It features basic insulation for a working voltage of 568 volt RMS, 800 volt peak, and 4 kV dielectric insulation. It's compliant to the safety standards IEC 62368-1 and IEC 61558-2-16. It's ACQ 200 qualified, and as mentioned, it features very low interwinding capacitance down to 7.5 picofarad for high common mode transient immunity. Here are some useful links for the online catalog of the WE-AGDT transformers. Currently, there are 6 transformers which form part of the series, and also another link for the product marketing video. And just to mention regarding automotive applications, so we have already said ACQ 200 qualification is completed. Automotive qualification, PPAP level 3, IATF 16949 is currently in progress. It will be completed in the future. So for automotive projects, the current WE-AGDTs, they can be used for development in pre-validation, but for mass production, then should wait to when the fully automotive qualified parts are released and are included in the automotive standard products from Würth Elektronik. So thank you very much for your attention. If you have any questions, please type them in and we will try to answer them.
Yes, thanks a lot, Eleazar and Emil. As you already mentioned, we would like now to turn our attention to your questions. So, yeah, feel free to ask and enter them in the control panel. Let's see, maybe one first question. Do you have any transformers to drive 600 volt gun FETs with 5.5 volt and -2 volt?
Yeah, I can answer that question. At the moment, we don't have a transformer which is optimized for these output voltage levels. I mean, a reference design with a flyback topology like this one. However, we have received this request already in the last months, 2 or 3 requests already regarding high voltage gun devices. So we are working on a reference design optimized for these output voltage levels. The final, it might be 6 volt -3 volts that we design at the end, but it's still not decided. But what we want to optimize with the reference design, so we need to take into account that gallium nitride FETs, they can switch even faster than silicon carbide devices. So minimizing the interwinding capacitance of the transformer becomes now even more important. So we will optimize this design. We will use a primary cell regulated flyback topology with the same form factor like the RD001 design, with EP7 also transformer, but we will optimize it for a lower interwinding capacitance in order to achieve even higher CMTI. So it will be released in the future. We cannot say when at the moment, but we are working on it.
Sounds good. Thanks. Another question, does a higher rated isolation also helps with CMTI?
Okay, can you hear me? Okay. I would like to answer to that question. I think it's a good one. I would say indirectly, yes, a higher rated isolation also help with CMTI. And why I say that is because when we talk about higher rating isolation means that we have actually more isolation, more separation between the primary and secondary windings. Therefore, the distances being bigger between the two primary and secondaries, indirectly or directly, the capacitance is lower. Therefore, this will help with CMTI. I hope this helped answer to the question.
Thanks for answering. Maybe one last question. Is the flyback topology superior to the others when the input voltage is not constant?
Okay, I think I can answer to that one as well. Anyway, thank you for the question. As you already suggested, from it, I would say the flyback is optimal choice when we have to deal with variable input voltage. I think Eliasar clearly stated there in his slides. For example, like battery voltage, where it change with the level of charge. Yes, we can use also other type of topologies that we mentioned there, like push-pull, half-bridge, and resonant LC, but a pre-regulation is necessary. This pre-regulation can be done with a linear regulator, and as small as they are, they dissipate heat, especially when needs to handle substantial input-output voltage differences. Therefore, care should be taken for component spacing to offer the necessary thermal relief, and to not mention the overall efficiency. There could also be used switch mode power pre-regulator with very little losses, but like buck stage. But this also requires extra space due to extra components, like an extra inductor, and also will add some EMI issues. So despite a bigger transformer, as it needs to store the energy, overall, I will say a flyback, it's the optimal choice for compactness and handling variable input, and as well regulated output voltage rails. I hope this answered to the question.
Yeah, thanks for answering it. And thank you both for your interesting presentations. I would say if there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed the presentation. The next presentation topic is unleashing GaN with high performance gate driving from our partner Mindset. And this presentation will start at 4 p.m. So hopefully see you there and enjoy our digital days. Goodbye.